educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on periodic motion. In our last lesson, we learned about simple harmonic motion, or SHM. Today, we will discuss the relationship between SHM and uniform circular motion. We will also study equations that determine displacement, velocity, and acceleration. Are you ready, students? Let us begin. Last time, we reviewed the sinusoidal graph of simple harmonic motion. Let us start today's lesson by discussing a different figure, the circle. Here we see a point, P, moving around a circle of radius, A. P begins at point C and moves up through the angle theta. To find the height of P, we can use the trigonometric function sine. Height is given by A times sine of theta. Now we need to introduce a new quantity, angular speed. Angular speed, or angular frequency, is denoted by the symbol omega. It represents the rate of change of an angle turned with time and is measured in radians per second. We can rearrange this equation to define theta as angular frequency multiplied by time. Now we can rewrite the equation for the height of point P as height equals radius A times the sine of angular frequency multiplied by time. You probably recall, students, that 2 pi radians is equal to 360 degrees, or in this case, 1 complete oscillation. Thus, 1 complete cycle turns an angle of 2 pi, and the angular frequency can be calculated by 2 pi times frequency. 2 pi times frequency appeared in our previous equation for displacement. Therefore, we can conclude that the height of point P going around a circle and the displacement of an object performing SHM are the same. Let us now move on to discuss velocity, acceleration, and displacement. The velocity of the oscillating mass is the rate of change of displacement. For example, at the top of a pendulum swing, the velocity is 0. It is the highest when the oscillating object passes through the equilibrium position. This can be seen on the displacement time graph. When displacement is the highest, velocity is the lowest. In general, velocity can be found as the gradient of the displacement time graph. The equation of the oscillation shown in this graph is x equals amplitude times sine of angular frequency multiplied by time. Therefore, the velocity is found by angular frequency times amplitude times cosine of angular speed multiplied by time. The maximum size of velocity is found by angular frequency times amplitude. Students, let us take a few minutes to practice the equations we have learned so far. Suppose that an object moves with simple harmonic motion of amplitude 16 centimeters and a time period of 1.2 seconds. Please calculate the frequency, the angular frequency, and the maximum velocity of the object.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, everyone. I hope that you were able to recall the correct equations. To find the frequency, we simply divide 1 second by the time period of 1.2 seconds. Therefore, the frequency is 0.83 hertz. To find the angular frequency, we divide 2 pi by the time period. Therefore, the angular frequency is equal to 5.23 radians per second. To find the maximum velocity, we multiply the angular frequency by the amplitude. Our answer is 0.84 meters per second. Well done, students. Now, let us move on to acceleration. From previous studies, you know that acceleration is the rate of change of velocity. The equation for acceleration is the negative value of the angular frequency squared multiplied by the amplitude times the sine of the angular frequency multiplied by time. The maximum size of acceleration is the negative value of the angular frequency squared times the amplitude. This equation is obtained when the mass reaches its maximum displacement. Recall, students, that the equation for displacement looks like this. We can substitute this value into the equation for acceleration. We find that acceleration equals the negative value of the angular frequency squared times the amplitude times the displacement. This is the defining equation for simple harmonic motion. Let us go back to the object from the previous activity. Students, please find the maximum acceleration of the object. Then, using the cosine equation, find the object's displacement after 0.5 seconds.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. The maximum acceleration is found by squaring the angular frequency and multiplying this number by the amplitude. We get 2 pi over 1.2 squared, which is 27.4 multiplied by 0.16. The maximum acceleration is negative 4.39 meters per second squared. The cosine equation for displacement is amplitude times the cosine of the angular frequency times time. Therefore, by substitution, we get 0.16 times the cosine of 2 pi over 1.2 times 0.5. This gives us 0.16 times the cosine of 2.62. After 0.5 seconds, the displacement is 0.16 meters. Did you notice that your answer is the same as the amplitude, students? This seems logical because after half of 1 second, the object will have been displaced by half of the cycle. Today, we have learned how to relate circular motion to simple harmonic motion. We have also learned how to express displacement, velocity, and acceleration by using angular frequency. In our next lesson, we will study resonance and forced oscillation. Until then, thank you, teacher. Thank you, students.